So far, we've set up some apparently quite complicated algebraic expressions, and we've not done much with them, and you may be thinking that this is going to be a very complicated theory to apply. Actually, now we've done all this mathematics, it's fairly simple to use perturbation theory. One very important reason for the simplicity is that with perturbation theory, we almost always use it only to the first non-zero order. Often, first-order perturbation theory may be enough. Sometimes, first-order perturbation theory gives us just a zero result, that there's no change in our system when we perturb it, at least as far as the first-order perturbation theory is concerned. This can often happen when we have a system that starts out by being symmetric. In such systems, though, the second-order effects are usually non-zero. And nearly always with this time-independent perturbation theory, we can stop there. It would be unusual indeed for a system to have no response in either first or second order perturbation theory. So let's now apply our perturbation theory to our example problem of an electron in a potential well with an applied electric field.
So let's look then at our example problem of a potential well infinitely deep with an applied field. So we write our Hamiltonian as the sum of the unperturbed Hamiltonian, which inside the well in our dimensionless units was very simple. It's just this expression here. And the perturbing Hamiltonian, which was our linearly varying potential that resulted from the field here in dimensionless units. So that rose steadily from one side of the well to the other with position c. And again, for our calculation explicitly, we're going to choose f equals 3. So we can compare with our previous calculation. In first order, the energy shift with applied field is just given by this simple expression here. And that reduces to this integral. Well, that integral is basically c minus a half times sine squared m pi c. But that's 0. It's 0 because the sine squared function is even with respect to the center of the well, whereas the c minus a half function is odd, and this is true for all m. Hence, for this particular problem, there's no first-order energy correction. Why is that? Well, there's no first-order energy correction because of symmetry. Here's our problem. Before we put the field on, we've got our usual infinitely deep well. This is the first energy level within it. If the energy changed proportionately with applied field, suppose for some reason it went down here, changing the field direction, or the sign, would change the energy correction sign as well. Truly, if the change in energy is proportional to the field, then if it's negative for a positive field, then it's positive for a negative field, or vice versa. But by symmetry here, the energy change cannot depend on the field direction. This problem here is really not any different from the one where the slope is in the other direction. This is a symmetrical problem to start with. So there can't be any first-order correction to the energy. It would have the wrong sign in one direction. The general matrix elements we're going to need to go further with our perturbation calculations are these matrix elements here. Sometimes we write them down with this shorthand. Actually, for these calculations here, we'll mostly write them out completely in this bracket form. So these are the integrals. And in general, to get any non-zero result out of this integral, we need these integers u and v in here to have opposite parity. That is, if one is odd, the other must be even. Otherwise, these matrix elements are going to be 0 by parity arguments. And that's because the overall integrand would be odd about the central point, c equal to half. So we can proceed to calculate the first-order wave function correction using these matrix elements for the first state. So we're going to choose the perturbations to the first state inside this well. Well, here's our expansion, where these are the formulae for the coefficients. And in our dimensionless units here, these energies, epsilon naught n, are just n squared. That's the usual quadratic spacing of the energy levels in an infinitely deep potential well. And that's before we put the perturbation on. And in practice, we're going to have to choose some finite end to our summation. The computer can only keep going so long. So instead of this going on up to infinity, it's going to stop at some finite number, just for practical reasons. And note, incidentally, also, because we've chosen m equals 1, the n not equal to m in this summation means we can just start at n equals 2. Here we're going to choose q equal to 6. But actually, it doesn't make much difference if we make q a little bit smaller than that. So explicitly for our expansion coefficients then, for our AI1s, for 3 units of field, we have numerically these results. So A21 is 0.18, A31 is 0, and A41 is 0.003. Here, the value of 0.180 for A21 compares rather well with the value of 0.174 that we got above when we did a finite basis subset method. We can sum the zero-order unperturbed wave function, that's this one here, with its formula here, and we can add on to that the first-order perturbation theory correction from the second basis function that we just worked out. Here's our 0.180. Add the two of them together, and we get this orange curve. So this is our calculated, approximate, corrected wave function. And it comes from the sum of the unperturbed wave function plus this additional correction to it. So you can see this is positive here, so the orange curve is above the green curve. And this is negative here, so the orange curve is below the green curve. We could add in the next wave function up, but it's so small, the correction from that we don't even see it on this graph. So we get a fairly good approximation here to our wave function by taking just the first two of these terms. The second order energy correction, well, the first order one was 0, but to get a perturbation correction to the energy, we go to the second order. And explicitly, we have for our formula that the second order correction is for our first state, psi1 hp times the first order wave function correction. And formally, we can write that all out here. Again, we're summing just up to some finite q for purely practical reasons. And the numerical answer to this calculation is minus 0.0975 for 3 units of field. Or that means a total energy of the unperturbed state, which had an energy of 1 unit, plus the first order correction, well, that was 0, plus the second order correction, this number here, so that gives us 0.9025. And that compares with our result of 0.904 from the finite basis subset method, for example. Now, one of the great benefits of perturbation theory is that it gives us formulas. So far, we've only been working out the answer for a very specific field, but in fact, perturbation theory will give us a formula for the answer. Note that this second-order energy correction, for example, is analytically proportional to the square of the field. So in this matrix element here, we've got the field buried inside there. Here it is explicitly. So we can pull that out as a square out the front. So this is a number that we can work out. This summation here is just a number multiplying the field squared. So we've now got a formula for the energy correction. Hence, perturbation theory gives an approximate analytic result for the energy, which we can now use for any field. Explicitly, we can write the energy for the first state in this approximation in our dimensionless units as this energy, eta1, is equal to approximately the original unperturbed energy eigenvalue minus 0.108 f squared. That's the number we get from just summing up the formula in the previous view graph. This typical kind of result of perturbation theory gives us, as we said, an approximate analytic formula now. And this is valid, presumably, for small perturbations. Similarly, we can use the same technique for the wave function. The correction in this case is approximately proportional to the field, because actually it's the first order wave function correction we're using here. And for example, with expansion coefficients calculated with this formula here, We can pull the field out to the front here, and we're left with c minus a half in the middle. So our first order calculation here gives us something that's proportional to f for this expansion coefficient. So keeping only the dominant contribution that was from our second state wave function in our example, we would have an approximate formula valid for small f for the wave function, and here it is. It would be the unperturbed wave function plus a number which turns out to be 0.06 when calculating this all up here, times f times the second order wave function. This incidentally is not quite normalized. The way we've set up perturbation theory, we haven't also normalized the functions, but we could easily do that. We're not going to bother to do it here, but technically we should actually renormalize this wave function to get things dead right. However, because we're really only working for small corrections, it usually doesn't matter very much. So therefore, we can plot all this up. So we're going to run a little simulation here. This orange curve is going to anticipate the result for how the energy changes with field. For the moment, we're plotting the unperturbed wave function here and the component of the second order wave function, the second level, into the basis here. The second level from the basis set. Now at the moment that's 0 because our field is 0 and our wave function is just the unperturbed wave function. But we can run a little simulation here and see how the wave function changes with field and how the energy changes with field. So let's run that. So you see that progressively from our formulae we could calculate the energy as a function of field, and we could see how the wave function changed as a function of field.
So we see that perturbation theory is particularly useful for calculations involving small perturbations to the system and can give simple analytic formulas and values of coefficients for various effects involving weak interactions. It's also conceptually useful in understanding interactions in general. For example, we can use perturbation theory to judge whether or not to include some level, for example, in a finite basis subset calculation. Perturbation theory tells us that if the level is far away in energy or has some matrix element that's very small compared to some closer level, we can safely neglect that farther level because of the large energy separations that appear in the denominators of the perturbation terms. The concepts of perturbation theory are giving us a guide as to what basis functions to include in our finite basis theory method. It's quite generally true of many different approximation methods that energies can be calculated reasonably accurately even with relatively poor wave functions. This is something that we can also understand based on our experience with perturbation theory. There we see that the nth approximation to the energy only requires the n-1th approximation to the wave function. As we said, generally perturbation calculations are most useful for the first non-zero order of correction. And for time-independent problems, nearly always second-order perturbation theory is as far as we ever need to consider. Sometimes specific effects require higher-order calculations, and this is true of some so-called nonlinear optical effects we can encounter in time-dependent perturbation theory. For example, the velocity of light propagation in optical glass fibers changes a little as we change the brightness of the light we shine into the fiber. This is a perfectly real and somewhat annoying effect that we can see in optical fiber communications. Describing that particular phenomenon actually requires third-order time-dependent perturbation theory to explain it, and those models work quite well. Generally, as I said, it's best to stop at the first non-zero order in perturbation calculations. Trying to improve the result by including higher-order terms is not very productive. This particular kind of perturbation method we are discussing, which is known as a Rayleigh-Schrödinger perturbation theory, tends to lead to a series that does not converge very rapidly. So in perturbation theory, we usually content ourselves with the first useful result we get for some specific effect. Those results can be very useful, however, both conceptually and practically.